Welcome to The Explainer. Today, we're going to dive into this really powerful framework, a new way of thinking that completely changes how we analyze and even design these incredibly precise machines that honestly shape our entire modern world.
Okay, so what are we even looking at here? These are flexure mechanisms, and they're amazing, right? They bend and flex to create motion that is just perfectly smooth, perfectly repeatable. We're talking about things like space telescopes, atomic force microscopes, the really high-tech stuff. But here's the catch. For the longest time, designing them was kind of a shot in the dark. You'd use these super complex simulations that were basically a black box. You'd put your design in, numbers would come out, but you never really got that gut feeling, that intuition for why it worked. So that's the big question, isn't it? How do we crack open that black box and get a model that actually gives us real design insight?
And to answer that, we've got a clear roadmap. First, we'll look at the world of precision. Then, we'll learn a new language. We'll get into the building block method, figure out how to assemble complex mechanisms, see what's in the designer's toolkit, and finally, check out the proof and the payoff. Let's get to it.
All right, Section 1, the world of precision. So what's the real challenge here? It's all about mapping the relationship between a force you push on something with and how that thing, twists, bends, and moves. The goal is a model that doesn't just spit out a number at the end, but actually shows us why it's happening.
And this slide just lays it all out so perfectly. We're taking a systematic, bottom-up approach. Think about it like this. Step 1 is the foundation, right? We need to learn the language. Step 2, we create a library of building blocks, our Lego bricks, if you will. Step 3, we learn the assembly rules, how to click those bricks together. Step 4, we actually build the system. And finally, Step 5, we have to prove it all works. Simple, elegant, and super powerful. Okay, so let's get to that foundation, a new language. See, to really talk about complex 3D motion and all the forces involved, our normal day-to-day language just doesn't cut it. We need something more precise, a special language. And that language comes from this really cool field called screw theory. So in this new language, it's pretty straightforward. Any kind of motion, a mix of rotating and moving side to side, we're going to call that a twist. And any kind of load, a combination of forces and torques, we'll call that a wrench. Simple enough, right? But the key, the thing that connects them, our Rosetta Stone, is this one elegant equation you see right here. It says the twist, the motion, is equal to the compliance matrix C times the wrench or the load.
And you've got to understand, this 6x6 compliance matrix, it is not just a boring grid of numbers. No way. Think of it like a complete instruction manual for how any part is going to behave. You tell it what force or moment you're applying, and boom, it tells you exactly how it's going to move. It's basically the DNA of the part's flexibility. It's everything.
All right, so we've got our language down. Now for the fun part. It's time to start creating our library of parts, our Lego bricks, and figure out the rules for snapping them together to build something way more complicated.
And here is where you can really see the power of this whole idea. Let's take our very first building block, a simple blade flexure. Now look at its compliance matrix on the screen. This is so cool. Every single number in that grid means something real, something physical. This one tells you how it bends, that one tells you how it stretches, and this other one over here, that's torsion. See? It's not a black box at all. It's a crystal clear blueprint.
Okay, but there's one little wrinkle. If you're going to combine different blocks, they all need to be speaking the same language, right? They need to be described from the same point of view. It's like giving directions. Everyone needs the same starting point, the same "you are here" map. A flexure's compliance totally depends on where you're measuring it from, so we use the special math tool and a joint transformation matrix to basically shift every part's perspective into one single universal coordinate system. That's the trick that lets us actually add them all together.
So our first assembly rule is super intuitive. When you connect your parts end-to-end, what we call in series, the whole thing just gets more flexible. And to figure out the total compliance, you just add up the compliance matrices for each individual part. It's really that simple. It's exactly like hooking up a bunch of springs in a line.
And the second rule, well, it's pretty much the exact opposite. When you put parts side by side or in parallel, they team up to resist motion, and the whole structure gets stiffer. Now, in this case, you don't add the compliance, you add the stiffness, which is just the flip side of compliance. The best way to think about it is like a bunch of columns all working together to hold up a roof.
Okay, let's recap. We've got our language, we've got our building blocks, and we've got our assembly rules. We have the complete toolkit. So now, I think we're ready to move past the simple stuff and tackle a really complex real-world mechanism.
And this is our target, this spatial compliant platform. It is just a brilliant piece of design, mainly because it's a hybrid system. Check it out. Each of its 3 legs is a serial chain of flexures, one after the other. But the 3 legs themselves, they're arranged in parallel to hold up that top platform. So the question is, how on earth do we analyze this?
Well, the way forward is to just deconstruct it using the rules we just learned. It's a 2-step plan. First, we tackle the serial part, we'll analyze just a single limb, then we tackle the parallel part by combining 3 of those limbs to understand the whole platform. Simple as that.
And here's how we execute that plan step by step. First, we start with the stiffness of one limb. Got it. Next, we use our transformation matrices to make sure all 3 limbs are viewed from the platform's center. Then we use our parallel rule. We just sum up all the stiffnesses. And for the final step, we just flip that total stiffness matrix to get the final compliance for the entire platform. Done.
Okay, and this is where the real magic happens. So far, we've mostly been talking about analysis, right? Figuring out the behavior of a design that already exists. But the true power of this whole framework, it's not just an analysis tool. It's a full-on designer's toolkit.
This slide really brings it all home. Because our final model isn't just a number, it's a symbolic equation. We can do some incredible things. We can instantly find the platform's center of rotation. We can play around and ask what-if questions. Like, hey, what happens to the compliance if I change the leg angle? But even better, we can do what's called synthesis. We can work backwards. We can literally say, I need the platform to move in this exact way, and then solve the equations to find the precise dimensions you need to build it. That is a game changer.
Now, this all sounds great. It's very elegant, very neat. But you know what the big question is? Does it actually work? Does this theory hold up in the real world? Well, let's take a look at the proof.
So to find out, a team actually built a physical prototype of this platform. And then they put our new symbolic model to the ultimate test. It was a 3-way showdown, our analytical model versus a super detailed, time-consuming finite element simulation versus the real physical thing. And the results, honestly, they were stunning. Just look at this table. The numbers from our simple analytical model, they match the predictions from that super complex FE simulation almost perfectly. For the most important factors, the error was less than 2%. That's incredible. It's all the proof you need that this approach is both powerful and incredibly accurate.
So let's just step back for a second and think about what this all means. We've officially moved beyond the black box. What we have now is a systematic toolkit that gives us real insight, a direct link between a design's shape and how it performs. It's way, way more efficient than running a new simulation every single time you tweak something. And the big one, it lets us do synthesis. It lets us design for a specific goal. This really does transform Flexure analysis from just a numbers game into a truly intuitive and powerful design science.
And that leaves us with one final big question to chew on. We've seen how a mechanism that looks impossibly complex can be totally understood just by breaking it down into simple building blocks with a few clear rules. So it makes you wonder, right? What other complex systems, in engineering, sure, but maybe even beyond that, what other systems could we understand in a completely new way if we just took the time to find the right language, the right building blocks, and the right rules for putting them all together?